So we're in the middle of the section on fluid kinematics, and last time I think I showed this diagram or a version of it, and the fluid body or a fluid element that would start off in a rectangular shape like this, not a rectangular, how about a square shape or a cube, can be viewed as undergoing four types of deformation or motion. So, and also you can contrast it with the solid body. So here's just a contrast with the solid body, but here's the fluid chunk. So we visualize it as undergoing a translation, if it's a solid, or rate of translation. So think about the velocity vector v, and it's moving at a certain rate in the x and in the y and in the z. So that velocity vector field describes its rate of translation. Then the other is, think about that object rotating. So not just translating in the x or y or z, but rotating. And here we just show it rotating about in the xy plane as shown in the counterclockwise direction. And so you could think about the rate of rotation. Well, how would you describe the rate of rotation mathematically? Well, it's the rate of change of the v component of the velocity with respect to x minus the rate of change of the u component of the velocity with respect to y. Take 1/2 of that. That's the rate of rotation. They introduce a symbol omega, and you can just use your right hand and put your base of the hand here, put the fingers pointed that direction, curl your fingers from the x direction into the y direction, and your thumb will be pointed in the positive z direction for a right-handed coordinate system. And so that's the rate of rotation about the z-axis, the little fluid element in the xy planes rotating around the z-axis. Okay. We also talk about linear strain rate. So how is it stretching in the x? How does the fluid element stretch in the x? And you can describe it by this epsilon xx. And so it's a rate of change of the u with respect to x. So if I move in the positive x direction, is it going faster in the x versus over here? Something like that. Then it would have a linear strain rate, be stretching it. Likewise, you could have it in the y direction. And then you could have a shear strain rate. So let me do this. How about this? Straining in the x, straining in the y. And so what you have is the epsilon exx. You have the formula, the rate of change of the u component with respect to y plus the rate of change of the v component with respect to x atom. And then take 1/2 of that, and that would be the shear strain rate. Well, just make sure and remember that the fluid undergoes 4 types of deformation, and you start to get familiar with this notation of taking derivatives of velocities, and they mean something that you can interpret those derivatives to help describe the rotation, strain, linear strain or shear strain of the fluid element. Last time, did we not talk about vorticity? What was the Greek symbol? Zeta. And what is the definition of vorticity?
It's a curl of the velocity field.
So we have del cross v is the vorticity. And we talked about how to calculate that curl of the velocity field. We typically set up a 3x3 and take the determinant of that 3x3 matrix, where the first is I, j, k, the unit vectors. The second, rate of change with respect to x, rate of change with respect to y, rate of change with respect to z. And the last is u, v, w, the 3 components. Okay, and then you go ahead and compute that determinant to calculate the curl of the velocity field. And then how is the vorticity related to the rate of rotation, omega? This is a vector entity, omega. 1/2 vorticity. So some textbooks will define the vorticity such that it does give you that rate of rotation. Some of them, well, you have to put a half factor in there. This textbook, I believe, has that half factor in there. Okay. You can take a look at hypothetical fluid flow fields. Here's one. They describe the velocity in the theta direction. So here's your r, and so at any point, let's say along this line, the velocity in the theta direction is perpendicular to the r direction, and there it goes, and you can see the profile. As you get further out from the origin, it's linearly increasing. So this is described just by omega, the rate of rotation in a circle, times r, the radius from the origin. It's really a solid body rotation. That's how you describe this flow field A. It's a solid body rotation. And then you would just say, okay, well, tell me what the vorticity is, and you calculate it, and you find that it's 2 times the rate of rotation. It's 2 times the rate of rotation, or omega is equal to 1/2 the vorticity. Okay? Well, this would be a rotational flow field. Sometimes you'll hear this term irrotational. So the ir in front of the rotational means not rotational. You can have an irrotational flow field. Okay, well, what would an example of an irrotational flow field look like? Well, try and do this. Put use of theta is equal to k divided by r, some constant divided by r, such that it's very fast right here, close to r equal to 0, and it drops off as r increases. That's that velocity profile. Okay, put that into our calculation to calculate the vorticity for this different, let's call this flow field B, following the textbook. Flow field B, and you find that the vorticity is 0. So if the vorticity is 0, it's not rotating. And the way you can visualize it is drop a coin or something that's going to float, a little marker. And the marker has some north, south, east, west, and then see if the north always points north as it's flowing in that flow field. Or in this example, they drop a smiley face, and the smiley face is looking straight at you. But in this flow field, as the smiley face is moving, the face actually rotates. So that's a rotational flow field. But in this other mathematically generated flow field, an irrotational flow field, you drop the smiley face, and as it flows, the smiley face doesn't rotate. It's always straight north, south, east, west. It maintains the same orientation even though it's changing location. So, irrotational flow fields. Reynolds transport theorem. Well, a lot of times it's abbreviated RTT. In some textbooks, it's not given the elaborate name of Reynolds transport theorem. It's just derived and shown. Let's go ahead and derive it or show it. Start out by saying, what is exactly my system? And in coming out of thermodynamics, you think about a closed system. What do you mean by closed system? In this textbook, they just say it's our system, but it's a closed system. Meaning, from your background, what does that mean?
Mass cannot flow across the boundary.
It's a fixed, you're focusing your study on a fixed chunk of fluid mass, and you're not letting the system go down in mass or up in mass. There's no flow of mass across that boundary of that system. The system is a controlled mass. Okay, so here's our system. Let me just try and draw it here. Okay. Now, we can compute things like volume and area integrals, and we follow that system as it moves and distorts. Well, let's first go back and say, if this is my system, could I compute something like a volume integral, and what would it look like? Well, the textbook puts this sort of V in there for a volume. It's hard for me to draw that V. But if you look at the textbook and the equations in the textbook, they use a symbol for that V. Well, that V can be confused with some V like this. What is another use for V? What? Velocity. So volume, velocity. So sometimes what I'll do, and the textbook doesn't do it, but I think it's common, is some people put something like that. Now, what's that symbol say? This V is not a velocity, but that V is a volume. Okay, so first of all, if you wanted to do an integral, it's a sum over all the little elements. And so if you're doing a volume integral, you're summing up over all of the little volumes. And so it would be something like this, dV. So I'm going to sum up over all the volumes of what? Well, whatever the integrand is. Okay, different analysis, different integrands. But I would do this over the entire system. Okay? At this point, sometimes you add a little descriptor right there. Sometimes we'll say, oh, do that integral over the control volume. Sometimes we'll say that. Okay? But right now, just know that you have to clearly identify what is the volume that you're summing it over. Okay, now if somebody says the integrand is rho, well, what is the units on rho? What are the SI units? Kilogram per meter cube. What are the SI units of a little dV, a little volume? Meter cubed, a small little volume. And so it looks like that volume integral would be a mass integral. You'd sum up all the little chunks of mass that constitute the system. Okay. Let's see if I can change this a little bit. Well, maybe, yeah, I might as well do it. We have a system often, in physics, in that we have a system which is just a particle. And that particle can have certain properties. It can have the mass of the particle, true? And then we could also have something like the property of the velocity of the particle. The velocity of the particle is important, but also the elevation of the particle, true? So you have things like elevate. What's the elevation important for a particle? You may think about, and you've solved problems in physics where the gravitational potential energy of that particle is considered. And then you have a conservation of energy principle or balance applied to that particle, and it may change elevation. Well, it may also change not just the gravitational potential energy, it may change kinetic energy. And so the velocity is important in the calculation of the kinetic energy of the object, right? All right. We also studied in physics that the velocity is important to the understanding of not just kinetic energy, but also momentum of the particle. What do you mean by momentum of the particle? Well, do you remember momentum of a particle? Somebody says, I have this chunk of mass. I'm holding up a book, right? And this book is moving at a particular speed or described by a velocity. What is its momentum? Well, you have two momentums. Do you want to talk about the linear momentum or the angular momentum? Linear momentum. Make it easy. Okay. So what's the linear momentum of a particle mass m moving at speed or velocity v? Do you remember that? So sometimes the linear momentum, maybe I shouldn't abbreviate that. Linear momentum has a symbol, maybe sometimes people put a P on it, and it's mv. What physics class did you take and they described the momentum as a vector? Did they? No? And if they did, well, if they didn't describe it as a vector, then you have to struggle with what symbol. I mean, sometimes it'll be like L for mv, the linear momentum. But forget it, right? What other momentum is there other than linear momentum? Angular momentum. And so it's around an axis that you're interested in. But I even hesitate to bring up linear momentum, but we will do it. We have to do it. There's a lot of fluid mechanics problems analyzed successfully using the principles of linear momentum, as well as angular momentum, as well as energy. But linear momentum is used. Just like mechanics and dynamics, they used linear momentum. You had the great conservation of linear momentum. Okay, so somebody says, this little chunk of mass, if I wanted to not just sum it up to get the total mass of the system equal to the integral of dm, maybe I wanted to get the, I don't know what symbol to introduce, P of the system. What's that? The linear momentum of the system? What would I do? What would I put inside this integrand right here?
Velocity.
Yeah, just the velocity. Now that turns into like a vector entity, the linear momentum of the system. If I'm only interested in the x direction, then it's a scalar equation. Well, you can then expand it back to a volume integral. This is a mass integral. This is a volume integral. So what would we put inside the integrand if I was interested in calculating the linear momentum of the system, not just rho? I would put v. True? True or false? Look good? Yeah, now, does it matter if I put v there or v there? No, it doesn't matter. You can put it anywhere, so it doesn't matter on the order. So those are some ideas for the volume integral. Also, if I had some energy per unit mass, maybe I could just use lowercase e for energy per unit mass. I could go and I could stuff it right in there. Whoop, there you go, energy per unit mass. And then if I did that integration over all the little masses of the system, I'd have the energy of the system, true? And if I did that, I could come up here and I could put that same E right there and integrate with respect to volume. Maybe I should have written that out. I hate to write out too much stuff, but if I'm interested in the mass of the system, it's the integral of rho dv or the integral dm. If I'm interested in the linear momentum of the system as a vector entity, it would be the integral of v as a vector, rho dv as a volume, or the integral of v dm. Okay, if I'm interested in the energy of the system, you integrate over the specific energy per unit mass, rho volume, integral E dm, something like that. We have to get used to doing volume integrals. I'm trying to give you some examples of them. Next one, area integrals. Well, when you do an area integral, you have to consider the outward directed orientation of the area. If I have an enclosing area, I have something that's on the inside and on the outside. If you're on the inside, that's my system. Everything that's inside that enclosing area is my system. And so the convention has been, and thankfully it is consistent throughout the literature, that we are interested in describing this area by an outward directed unit normal vector, and that gives us the orientation of that local area. And as we change locations, that outward directed unit normal vector changes as well. True? That makes sense? So the outward directed unit vector, it's not inward directed in half the textbooks and outward directed in the other half. Thankfully, it's always outward directed in every textbook I've seen. Doesn't mean somebody doesn't have a new idea and says it would be a whole lot better if it was all inward directed. And there you go. He writes a textbook on it. But everything is outward directed. So if I'm interested in doing an area integral, it's very important to get that orientation of the area, especially if I'm interested in flow across the boundary of that area. And mostly that's what I'm interested in. So I go and I have, I draw off a little chunk of area right here. And right here is its normal vector to that area. And right there I'm trying to emphasize it's perpendicular to the little dA. And I'm visualizing this as the little dA. Okay? Some other areas oriented like this. True? And what would the outward directed normal vector look like? Something like that. It'd have to be perpendicular to the local area. Here's another little area like this. And here's the outward directed normal vector, and it's perpendicular like that. True? See that? Okay. Now, what happens if I have a flow described by a velocity? I'm just going to show it. Maybe I'll show it like this. V. There's V. That's the fluid that's cutting across that little chunk of area. Maybe I have the same V cutting right there and the same V cutting right there. And maybe I should have shown another area. Maybe I'll do one more area like this. And here's the outward directed unit normal. And here is V for that area. It's the same. I'm trying to show the same V for all of these. True? See that? Okay. So you have to say to yourself, which one has for the same size, dA, has the greatest flow across it? Case A, B, C, or D, and I'll ask that as a clicker question. Which one of these cases, as I've shown, has the greatest flow rate across it? V is the same vector in all those cases. Same magnitude, same orientation. The size of the little dA is the same, the orientation's changed. All right, let's see. Congratulations to the majority, they got it right. Why is case B the greatest? Why is B giving me the greatest flow across it? They're in the same direction, so that it's like I'm trying to think of an analogy, but the flow is going all over that whole area. It's like the widest opening for that flow to go across. Okay. Which case gives us the lowest flow rate? D, right? The lowest magnitude. I didn't want to do positive, negative. Okay. As I've shown, are all of these positive across it? Let's say this is the inside, isn't it? This is the inside, this is the inside, and this is the inside. True? Because it's outward directed unit normal vector. That always shows you then it's flowing out in the direction of the little n. So aren't they all outward directed? What happens if I would change it and I would say, okay, here is a different area, and this one, the n is directed that way, and the V is directed that way. From the orientation of N, I know that this is the inside, isn't it? And I know then it's not flow going out of the control volume, but actually flow coming into the control volume in this case. True? Okay. Now, so we have this idea of the little outward directed unit vectors. We also have the size dA. We have its perpendicular, and then we want to know, how do I mathematically compute this flow? What is the mathematically, if I take this vector v and I dot it with n, that picks up the component of v that's in the direction of n. True? If I then multiply that by dA, what do I get? I get the velocity that's perpendicular to that area, so I have the little volumetric flow rate. This is a volumetric flow rate. Right? And it's volumetric flow rate out of the control volume. Can the vector product, this dot product, v dot n, can it ever be negative? Can it range from a large negative to 0 to a large positive value? Or does it go from positive, does it have to be positive only, like 0 and up? Can this result be negative? Yeah, in which case is it negative? Case A, B, C, D, or case E? E, it's negative. So this is a volumetric flow rate out to the control volume. In some cases, if I compute a negative entity, it's not a positive out, it's actually a in, because it's a negative flow rate. What SI units would this volumetric flow rate have? Something like meters cubed per second? Would that be the right units, volumetric flow rate? Sure. And so now that we have this idea of a flow rate going out, what we would do is, to get the net flow rate out, we do a summation. The summation is an area integral. The simplest area integral is V dot N dA over all of the area. Just like you have to integrate over all the volume, you have to integrate over all the area. True? I left a little room in here. If that was 1, you just calculate a volumetric flow rate. What would I have to put in there in this integrand to be a mass flow rate? True. What would I have to put in there to be not just a mass flow rate, but an energy flow rate that's going with that mass? E. This same E down here, which is our energy per unit mass. Energy per unit mass, right? So you can now, once we get this area integral, we can get the volumetric flow rate, we can get the mass flow rate, we can get the energy flow rate that's crossing that boundary because it's going with the mass. There can be a shaft energy flow rate across the boundary later. And it could be a heat transfer energy flow rate across a boundary later. But right now, if you can have energy flow with the mass. One other thing you can do, what's this, P? Linear. You can have a linear momentum flowing with that mass in or out of the control volume. What would I put right here? Would I put a velocity? Yeah, the velocity is already in there. That's why when you see these equations, you scratch your head and say something must be wrong, because it looks like the velocity is double counted for. But let's take it out and go slowly. What is that integral by itself? Volumetric flow rate. What is that integral? Mass flow rate. What is that integral? Energy with the mass flow rate. And then the last, most difficult, linear momentum flow rate. And forget the angular momentum. We can do it. I just don't want to overload you. Are you already overloaded? So we have this concept of the volumetric flow rate, the integral of V dot N dA. What exactly is this little n? It's a unit vector pointed in the outward direction for that enclosing surface that encloses a volume or some focus or system or focus of our study. Okay, it's a unit outward directed normal vector. Okay, what is this dot? Dot product, two vectors. We know how to dot product two vectors. What is this V? Velocity at that location where you're summing all over the surface. That V can change, that N can change as you do a integral summation over all of the little areas that enclose or make up the surface. Okay, when I put this parenthesis right here, the resultant of a vector dotted with a vector is a scalar. It's a scalar. It's just number. That scalar can be negative. That scalar can be 0. That scalar can be positive. If it's positive, it indicates there's outflow. If it's 0, no flow. If it's negative, inflow. True? Okay. Once we got that volumetric flow rate, then we start say, okay, how do I get the mass flow rate? Well, you put a rho V dot N dA, integrate over all of the area. And then we could do the energy flow rate, which is the integral E rho V dot N dA. And then we could do the linear momentum flow rate, which is the integral of V rho V dot N dA. Is this V right here the same as that V right there?
Yes.
Yes, they are. This resultant gives me a scalar. True? Rho times a scalar gives me another scalar. True? A vector times a scalar gives me a vector. So when I do this area integral, what is my result? I get a vector result. So when we deal with this linear momentum flow rate, it's a vector entity. Linear momentum in general is a vector. We can always work in 1D, drop it back, but it's a vector. So these are the same. Mass flux. What does this word flux indicate?
Fancy word for flow.
Flow. Perpendicular flow. Flow across an area. So it's across some area. So flow. So let's say I'm interested in the mass flow per unit area. What type of SI units do you think this mass flow per unit area has? Kilogram per meter squared per second. Does that make sense? Yeah. But first time you see it, you think, what, this is crazy. But it's a mass flux. It's a flow rate per unit area. It's going across that area. What is my mass flux from some of these terms that I've been introduced to? Is this mass flux equal to rho V dot N? Or is it rho V? Or is it rho V dot N dA. Oh, I don't know. Let's ask a clicker question. Answer A, B, or C, or D is none of the above. None of these. What do you think is something says, I want this mass flux? Okay, it's the mass flow rate per unit area. What is it? You know, in terms of some of these other things we've struggled with. Oh, we're all done. Let's see where we stand. Okay, we have quite a distribution, do we not? Sometimes you can rule out some answers by checking units. Okay, let's just say, what are the SI units of this first one? Kilogram per meter cubed times, what is the units on V dot N? Just meters per second, isn't it? It's just a meter per second. How about over here, kilogram per meter cubed, then you have meters per second. What about over here? I have kilogram per meter cubed times meters per second times, what's dA have? Meters squared. Okay. So, and then none, well, that's if we rule out these other cases. But let's take a look. Meters cubed go. So C has units of kilogram per second. True? Let's drop C. C is not a contender. It doesn't have the right units. All right. These have the same units. True? Okay. If it's a mass flux, it's a flow rate per unit area. Could I have an area that has no flow across it? Could I have an area with no flow across it? Yeah. In that, it could be where the area is pointed this way and the velocity is pointed that way. If it has no flow across it, what is the mass flux? 0. True? So, but if I don't account for the orientation of the area, which one does not account for the orientation of the area? Answer A or answer B? B. So answer A accounts for the orientation of the area. And so that dot product gives me the normal component of that velocity field. So it's what's going across the area. Remember, it's got to cross the area to make sense for a mass flux. So it looks like A looks like the best answer. Make sense? All right. Reynolds transport theorem. Well, this is a very general derivation. I think I have it worked out on another slide. Let's just go through it. Here is my system, SYS. This fluid dynamics book says system. I'm going to say it's a closed system. It's a control mass. True? So it's my CM, control mass, which is system. All right. Now, that's at time T. Some later time, it's in a flow field. It's a very general system, very general flow field. It goes, and it's now there. That's at time T plus delta T. This is the standard derivation of the Reynolds transport theorem. So this is my distorted system, my closed system, my control mass at the new time, T plus delta T. I'm very interested in things like mass, energy, and linear momentum, and angular momentum. All right, but you can do this for general, okay? So you could say to yourself, I'm interested in any arbitrary, I think the book uses B. What's B? I don't know. They had to use a letter that hadn't been used too often somewhere else. So it's a property of the system, okay? So you could talk about B as some property of the system. All right. Well, you could also have lowercase b. What do you think the lowercase b is? Something, same word, property of the system. But instead of just saying it's a property of the system, a word in front of it. Lowercase b indicating intensive, indicating that intensive property, the way you make an extensive property, intensive property is divide by mass. And so it's specific property of the system. That means per unit mass. Okay. So if I wanted to, I could go back to this one and I could say, what's cap B and lowercase b if the property of the system I'm really interested in is mass? Well, it's m. B is m. Okay, well, what's the specific? You almost have to be told 1. Mass divided by mass is 1. It's almost too trivial. What about the energy? Cap E. Lowercase e. Okay. What would that cap E consist of? Well, it consists of the 3 components that we study in thermodynamics and used in a lot of mechanical engineering: internal, kinetic, and potential energy. And then you'd have it on a per unit mass basis with the lowercase e. What about linear momentum? We could introduce a symbol P, but what exactly is that symbol P? How would we compute the linear momentum of a chunk of, wouldn't it be m? Hey, we used m up here for mass. Why not be part of the linear momentum? M what? V. Is that true or false? And now that's the kicker. What is my lowercase b if I'm interested in linear momentum? And the linear momentum is mv. V. True? And I'm not going to go with angular momentum. That's enough. You can look it up. It's just the cross product. True? And you could also do entropy balance. Some books will put that in there too. You have mass, energy, entropy, you have linear momentum, angular momentum, and I'm missing something else maybe, some other thing that maybe you're doing a balance of. But so what we say is the system, the property of the system can change. True? But let's do this. The property of the system at time t is equal to the property of the system, let me draw this, at time t plus delta t. You see that the property of the system at time t, and you have the property of the system at time t plus delta t, but they could change, true? So how would it change? Well, you'd say, well, it's a property of the system at time t plus delta t minus the property of the system at times t. Isn't that rate of change? So that would be something like the rate of change of the property of the system with respect to time times the change in time. Does that equation make sense? I know I've kind of given you a quick, I want to write it as I try to speak it. Maybe the way you speak it is a little confusing, but what it says is I can look at the property of the system at some future time, t plus delta t. Change is the minus the property of the system at time t, and that would be approximated by the rate of change, blah, blah, blah. Okay, let's work this one out. You typically take this and you bust it into 2 components, and you bust this one into 2 components. And what I do is I introduce this overlap region, and that overlap region is called the CV. What? Reynolds transport theorem really just puts a link between a closed system analysis and an open system analysis. We've done the same thing in Thermo 1. Here it's more general, and a lot of times in fluids books they do this very general derivation. So there's my CV. What do you think CV stands for? Control volume. That's really going to be my generalized region in space that I'm going to focus my study on. And then they have all of this. What is all of this? And I'm trying to show little vectors for fluid flow coming, because at time t, all of this region that I just shown in purple, maybe we call it region 1, is not in the CV. But at the end of the time, it's going to be in the CV. It's all we'll have swept in. True? And then you come over and you say, what is all of this? That's a different region. Maybe I call that region 2 to contrast it with region 1. Okay, well, all of that fluid that's now in this region 2, it was inside the CV, but now it's swept out. At time t plus delta t, it's now out. So the system at time t plus delta t is what's in the control volume at t plus delta t plus what is in B, region 2. What's in region 2? See that notation? All right. Minus what is in the control volume at time t, and what is in region 1. Make sense? So then they just take these and they say, let's put the control volume at t plus delta t and the control volume at t, and then we'll put over here, we'll put B2 minus B1. We'll finally get that delta t over, that delta t over, that delta t over. And what do you think this first entity looks like? That looks like the time rate of change of what's in the control volume. And what does this second term look like? How much the rate at which it flows out. Okay, so this is an outflow, and this is the negative of an outflow, which is an inflow. Negative of the inflow. Now, if you're wanting to, we can apply our control, our integrals over a volume. Let's integrate over the control volume. So the property that's in the control volume at any instant in time is the integral over the control volume of lowercase b times rho times dv. So that is what gets the time derivative. And then we can combine these. This B2 was an outflow, B1 was an inflow. The negative of the inflow was an outflow. I needed to put a positive on that, right? The negative of the inflow is a positive outflow. Okay, so we combine that into one integral. It's an integral over the area of the control volume or the control surface. A lot of times people say integrate over the control surface of what? Well, rho v dot n dA lowercase b. So what we have is an equation that says the rate of change of the property of the system with respect to time can be viewed as how it changes in a fixed region of space and how it's being swept out, as well as that integral is over the whole thing. It's going to be a negative on the inflow with respect to time. That's the RTT. Oh, I forgot. What does the abbreviation RTT stand for?
Reynolds transport theorem.
Reynolds transport theorem. You could transport mass. You could transport energy. You could transport linear momentum. You could transport entropy, and you could transport angular momentum and probably some other stuff. But those are 3 is enough to deal with for us right now. Here's the more general derivation. I did the same thing. Do you see that? It's the same thing. And then I said, oh, for mass, the big V is the mass of the system, energy of the system, and linear momentum of the system. Sometimes L or sometimes P for linear momentum. But MV is linear momentum. Okay. And then the specific property, 1 for mass, there it is for energy, and there it is for linear momentum. And did we get the same equation? We have an integral over to control volume. We have an integral over to control surface. Probably the hardest one is to think about is that one. So you have that V dot N. Then you multiply by rho to get the mass flux. Multiply by area, get the mass flow rate. And then multiply by the specific property of interest to get the flow of that property with the mass. That's a lot to comprehend. I hope you got a lot. Let's keep on, huh? Keep your chin up, right? So we apply it to the mass balance equation. Next chapter, we'll start really right here. Because do we have any mechanism by which mass of a system, a closed system, is destroyed or generated? No. And so basically, that has to be 0 because mass doesn't destroy it or generate it. But we do have, on a focused region of space, you can have an accumulation of mass because maybe the density increases with time, goes down time. They have this for the control volume is fixed in space, or it can be a deforming control volume. I think the math is rigorous or difficult enough. Let's just have a fixed control volume in space, okay? Don't do a deforming control volume. Just fixed control volume. So that basically is it piling up and are you getting a higher density or density changing? That would be changing the mass in the system. And then you have how does it flow across the boundary? Is there a net inflow or outflow, or is it 0? You know, if the amount of mass is not changing with respect to time in my control volume, then the net in is equal to the net out. It has to be at any instant in time. And so this integral has to be 0 as well. Okay, so there you go. So from kind of a general Reynolds transport theorem where you observe that this has to be 0 because mass is not created or destroyed, you get this very simple equation, and we'll use that next chapter. Energy, I'm just trying to show you. This looks like the Reynolds transport theorem with energy being the property of interest, and we have that specific energy and specific energy. Well, how can energy come in or out of a closed system? Well, 3 ways that we studied. Heat transfer. Give me the sign convention. Q dot positive in. Great. Shaft work and boundary work. That system can be distorted. Okay? That boundary work is described a little, it's tricky, but it's P dV. But this is the flow. I'm describing it for a control system. So the V times P rho is just unity, but we like to put the rho there so that we can get the PV term in the surface integral. And then we bring that term over and lump it with this other surface integral. So we have the specific energy times or plus PV. That energy is U plus 1/2 V squared plus GZ. Guess what? The P plus PV plus U combined to make a new property that we call enthalpy, H. All right, this one right here, that doesn't have enthalpy in it, does it? But when it flows across the boundary, you have this boundary work associated with deforming a control mass, which you push over and put it into a new property called enthalpy for the mass flow rate across the boundary. Okay, here is our shaft work, here is our heat transfer, here is accumulation, depletion of the control volume, here's for the flow in and out of the control volume. It looks a lot more mathematical, it looks a lot more, but we're going to break it down and use it just like we did in Thermo 1, often for a system at steady state, maybe for a system that has no heat transfer, maybe for a system and no shaft. Sometimes there are shafts, sometimes there are heat transfer. Very rarely do we have a transient problem, but you could have a transient problem. Okay? And then typically one inflow and one outflow. So these general equations boil down to something much simpler, and we can analyze it. Let's see. This page we talked about a mass balance. This slide we talked about an energy balance. What do you think is on the next slide? Well, I skipped the entropy because I just felt overloaded. Linear momentum. And I skipped the angular momentum because I felt overloaded too. Okay? So linear momentum. And here is, okay, instead of introducing L or H, or not H would not be used, P, like that, I just said, okay, MV, I think the book stays with that. How can the linear momentum of a system change? How can the linear momentum of a system change?
Change with respect to time.
We have this equation. You know, that equation isn't always written that way. Sometimes it's written this way. Somebody asks you, oh, you studied engineering. I saw this equation. I saw that equation. Are they the same? Are those equations the same or not? What does this little sum mean? Yes, if they are basically the same. Sometimes we emphasize that it's the sum of all the forces. Make sure to account for all the forces acting on that object in order to predict, let's say, the acceleration of the object. Somebody else says, well, I saw an equation. It was written F equal to that. Is that equation the same? It is. And actually, it's very common. I mean, as engineers, we like, oh, F equal ma. And F has to be the sum of all the forces. Don't leave off any forces. If you don't leave off a force, you can't use that equation, right? You skip the force. No. But right here, it then does. If I have a system where it's not, the mass is not changing with respect to time, guess what? That can come out. But a lot of times they just leave it inside. Okay, there you go. So that's why you can replace right here for the linear momentum. The sum of the forces change the linear momentum of the system, of our closed mass system. And then if you want to put it into a control volume, you have this time rate of change of the mass in a fixed region of space, control volume, and then the flow over the boundary. This is in what chapter? Chapter 6. We're finishing 4. We got to get through 5 before we get to 6. So that's our summary of kinematics, fluid kinematics. We covered a lot. Eulerian and Lagrangian description. Which one do we prefer as engineers? Eulerian. Yes, there's some computer codes that use Lagrangian and all that we need to know. Either you track a particle or you have a grid and you just know what is happening as fluid flows, different chunks of fluid flow through different zones of your mesh or grid. Okay. You'll think about velocity fields and acceleration fields. Then we had this really difficult concept, material derivative. What's that all about? This brand new notation. True? It accounted for not only a local acceleration due to how it changes with time, but also an advective or material acceleration, if you want to use it. That's often how it's used. So it accounts for how it changes with respect to time. And then it had this v dot del on this operator. And that was the advective acceleration or vective change. Okay. What about streamline? Well, I know that there's a path line and a streak line, but basically steady state, we just say it's a streamline. It's where a chunk of fluid goes, its path. Okay. If you choose to, you can put a little stream tube around that streamline, and now I have a little control volume with no flow across the boundary of that stream tube, just inlet on the end and outlet on the other end. We have contour plots, be able to think about here's a region, that's a line of constant temperature, constant pressure lines, constant temperature lines, gradients. All right, velocity profile plots. If you have flow and you drop a bunch of little markers, then the markers flow and they move, and that's your velocity profile. True? All right. Velocity acceleration vector plots come out in grid. Here it is. There's my velocity at that point, velocity at that point, velocity at that point. Talked about different deformation of a fluid element, translation, rotation, linear, and shear strain. We introduced property of vorticity. It's getting very mathematical. And the Reynolds transport theorem applied especially to mass energy and linear momentum. You ready to move into the next chapter? I'm going to stop right here.